All right, one more set of problems for us to practice. And I think this is a really good set of problems. I'll be honest with you, if it was up to me, I probably would have some of these on the actual exam because I like some of these problems. And I hope you enjoy them as well. Let's get going. So the first problem. So the population, which we'll measure as P, of a certain fish is measured in tons and follows a logistic model. So P prime equals K times P times 100 minus P. Given that in 2010 the population was 50 tons and that in 2020 the population was 80 tons, then determine the rate of growth of the population in 2010. And there's a reminder here that says, hey, if we have this logistic model and our initial condition, then we know the exact expression for the population. All right. So it's always good to identify what is it we're after. And so we say, look, we're after the rate of growth of the population in 2010. That's what we're after. Okay, so that's what we need to find. Now, in some sense, that's very straightforward, right? Because the rate of growth is a derivative, and we know our derivative. It's P prime, K times P times 100 minus P. And in 2010, we had 50 tons, which means that our answer is going to be taking P prime, which is going to be K times 50 times 100 minus 50. So that's the answer, except one detail. What's K? So as soon as we find K, we plug it in, and we'll be done. All right, so we've got to find K. So how do we do that? Well, we're going to use the rest of the information here. So the good thing is it gave us the formula for the logistic model. And 50, well, we know that's our initial population. And so we're going to think of 2010 here as being time 0. And so think of 2020 as being time 10. So we probably need to use this other information, that in 2020 we're 80 tons. So we could say, okay, look, P of 10 is equal to 80. But we can also say, hey, we know that in general P of T is what? Well, M would be 100. That's right, it's right there. That's M, so it's 100. So 100. The initial population, P0, is 50. Divide that by 50, initial population, plus 100 minus 50 times e to the minus k, which we don't know, but we do know m. That's still 100. That hasn't changed. And t. And of course, we can clean this up a little bit. So for example, that's 50, 50, 50. Since you have all those being 50, well, we can cancel. And so we can just do a quick. So we can say, look, this is the same as 100. Divide that by 1 plus e to the minus 100 kt. So now we put it in here. So this would be t equals 10. So we get 80 is equal to 100 divide by 1 plus e to the minus 100 k times 10. Well, now we say, this is great. Here's an equation that only involves one thing we don't know. We don't know k. So once we get k, we plug it up here, and we're done. Okay, so, well, now it's just a matter of cleaning up. So, well, we'll go ahead and run through that. We still need to do it, right? We got to do the work. So, what are some things we can do? We can flip both sides. And so, let's just come over here. We can say that 1 over 80 is equal to 1 plus e. And 100 times 10 is 1,000. So, to the minus 1,000 k over 100. Okay, move that 100 across. So we'll move it over to here. So 100 over 80, that's, well, it's the same as 10 over 8, which is the same as 5 over 4. So we have 5/4 equals 1 plus e to the minus 1000k. Subtract 1. So we get 1/4 is equal to e to the minus 1000k. Well, if we flip both sides, this negative means really 1 over something. So that says we have 4 is equal to e to the 1000k. And now take a natural log. We get natural log of 4 is equal to 1000k. Or at the very bottom, we can squeeze it in here. We can come to the conclusion that k is equal to 1 over 1000 times natural log of 4. All right, so that goes back there. And now let's put it in, and we'll have our rate of growth. So we have 1 over 1000 times natural log of 4 times 50 times 50. Well, again, 50 times 50, that's 2,500. So, all right, that's 2,500 over 1,000 log 4. And, well, of course, we can do a little bit of canceling here. 25 over 10 is the same as 5 over 2. So, there we go. 5/2 natural log of 4. Great. That was pretty nice. And that didn't seem to take too long at all. No, not too bad. Okay, so there we go. That's number 1. Number 2. Solve x cubed plus 3y minus xy equals 0. So it's a first order differential equation. And we notice something. And of course, we always notice things. We're looking for everything, right? But here's something to see. We have ay prime and ay. And those are the only places that y show up. And when we see that, a single y prime, single y, they're not inside anything. There's nothing raised to a particular power or anything. We say, aha, this is linear first order. And so we'll solve it using the techniques of linear first order. So the first thing is we have to rearrange. And this will probably be something that we encounter where it's like, well, they may not give us the differential equation exactly in the most nice form. So we'll have to be adaptable. And by that we mean, look, we'll have to be ready for us to rewrite it in a convenient way. So let's move that across. So we could say x y prime minus 3y is equal to x cubed. So we're getting closer. We're not quite ready yet. And you might say, well, why not? Because if we're doing linear first order, we have to look and say, hey, that thing in front of the y prime needs to be a 1. It's currently an x. So we now divide by x. So y prime minus 3 over x, y equals x squared. Now we're ready. So we take our integrating factor by taking the term in front. Don't forget the minus. So we have e to the integral minus 3 over x dx. Well, that's going to be e to minus 3 natural log of x. All right, that's e to the natural log of x to the minus 3, because we can bring that minus 3 in, which is x to the minus 3. So that's the integrating factor. If you like, you could also write this as 1 over x cubed. Now, that says, okay, take your differential equation, this form here in particular, multiply everything by 1 over x cubed. So what we'll end up with, 1 over x cubed, y prime, minus 3 over x to the 4th, y, equals 1 over x. But the left-hand side, by design, this is what happens when you have linear first order, this is the derivative of 1 over x cubed times y. And you can even just do the quick computation to verify. All right, so we know that this is equal to 1 over x. So we're going to integrate both sides, and then we'll almost be done, right? So integrate with respect to x. And what do we end up with? Well, on the left-hand side, we have 1 over x cubed times y. On the right-hand side, natural log of x plus some constant c. And, well, finally, let's just multiply through by x cubed. So we get that y is equal to x cubed natural log of x plus some constant c, x cubed. And that's it, right? There's no initial condition. And so that is the solution. Great. Wow. Great problem. This is a fun one. We should have more of these, right? Well, we should have the right number of them. That's what we should have. Number 3. A Mass-Spring-Dashpot system. So if you don't like the word dashpot, you can just think damper, or you can just say mass-spring system. Keep in mind we might have a damper. There's no external force is being set up, which has a mass, which is m of 4, a spring with spring constant k of 9, and a dashpot damper, which has an adjustable damper constant. Okay, so we get to pick, how much damping goes on. Now, wanting to maximize the speed the system returns to 0 after a jolt, it has been determined C should be set so the system is critically damped. All right. So, in other words, you have this system, and you think of it like a car, right? You have a jolt, and it starts to move. Well, eventually, over time, you want it to sort of go back to where it started. Now, it might go lots of oscillations and take a very long time, or it might have some exponential decay. And the point here is that the fastest exponential decay happens when things are critically damped. So in some sense, critically damped is that sweet spot of saying, I want to get back to where I was as fast as possible. So, all right, great. Now, there's 3 parts, but mostly this is just sort of stepping us through the problem. So we have to determine the value C. We have to find the general form using the answer from part A. And we have to find the particular solution where we have some initial conditions. Now, the key thing here is there's this phrase. It's even been italicized, critically damped. Do we remember what that means? So we'll get to that in just a moment. So the Mass-Spring-Dashpot, the formula for it is mx double prime plus cx prime plus kx equals 0. And the 0 is because there's no external force. So we know m is 4, we know k is 9. So we have 4x double prime plus cx prime plus 9x equals 0. So now we come to what does critically damped mean? So remember there's things like underdamping, overdamping, undamped, and critically damped. And what they are basically come down to saying, what kind of numbers do you have showing up as roots of your characteristic polynomial? So that critically damped is that transition from underdamping, where you have that exponential decay, and at the same time of overdamping, where you just only have exponential decay. And so the key here is that critically damped is repeated roots. So that's what critically damped is. So repeated roots of the characteristic polynomial. So what happens? Well, we can come here. We can say the polynomial becomes 4r squared plus some constant c times r plus 9 equals 0. And we want to pick c in such a way that we have repeated roots. Now, there's a couple ways we could do that. Here's one way. We could say, hey, if we have repeated roots, this really has to have the form of ar plus b quantity squared. That's the only way we can have repeated roots. So that would take the form of a squared r squared plus 2ab times r plus b squared. And then we say, well, look, a squared, that's 4, and b squared, that's 9. So a has to be 2, b has to be 3. So this is 2 times 2 times 3, also known as 12. And now we know what c needs to be. Another way you could do this is say, all right, take this and throw it into the quadratic formula. So we have that the roots would be negative this term here, so plus or minus the square root of our this term squared minus 4 times 4 times 9 all over 2 times 4. Now, the only way we can have repeated roots is if this part equals 0. So that says, hey, we need that to go away. So that says c squared. Well, 4 times 4 times 9 is the same as, well, it turns out to be 12 squared. So that says c has to equal 12. All right. So in any case, we know the answer. So for part A, the answer is c should equal 12. And we'll just put it right there. And there we go. So we've done part A. Now, part B. Determine the general form for solutions using the answer from part A. So in other words, okay, so now we have that, look, c is 12. All right, what's our form? Now, here, we're actually in good shape. Now, we could come here, we can find the roots, or we can actually come here, right? Because we said our roots were going to be 2r plus 3 squared. So that says our roots are going to be minus 3 over 2 minus 3 over 2. So we say our general form will be x of t will be some constant a, e to the minus 3 over 2t. And now it's a repeated root, so we're going to do our bumping up. Some constant b times t times e to the minus 3 over 2t. And that's part B. Okay, so we've got A, we've got B. Part C. Find the particular solution with x0 equals 3 and v0 equals 5. Now, v0 is really a reference to the velocity, which means the first derivative. Okay, so we should compute x prime of t. So we'll do that here. So we'll have minus 3 halves a e to the minus 3 halves t plus b. Now, here, what will happen? Well, we're going to do a product rule. So the root of the first is 1 times the second. So we'll have 1. And then when we take the root of the second, we'll have a minus 3 halves come down. So minus 3 halves t, and that'll be e to the minus 3 halves t. Okay, so that's the derivative. So now we plug in our initial conditions. We know that x of 0, which is just our x0, is 3. Well, plug in 0 here, we get a plus 0. So we solve for a. Nice. All right. On the other hand, we have x prime of 0. Well, that's our v0. That's 5. Well, what is that? That's minus 3 halves times a. But, we know what a is, so we can go ahead and put that in. Minus 3 halves times 3. Plus, here we have b times 1. And e to 0 is 1. All right. Well, okay. That's not so bad. So we have minus 9/4 plus b equals 5. Okay. So b will be 5 plus 9 over 4. Well, okay. Sorry, why do I say 9/4? 9 halves. Ah, I can do math. 5 plus 9 halves. Well, that's 10 halves plus 9 halves, which is 19 halves. Okay. So that's A, that's B. So put it in, and we get our answer is 3 e to the minus 3 halves t, and then plus 19 halves times t, and e to the minus 3/2 t. And that's it. We're done. We're done. Wow! This was great. What a fun problem. What a fun problem. All right. Well, halfway done, right? Feels like we haven't even really started. I hope the test goes this well. All right, number 4. Given that y equals e to the 2x and y equals e to the x and y equals e to the 2x are solutions to the following constant coefficient linear homogeneous differential equation, determine a and b. See, we don't know what a and b are. They're not specified. But we say, hey, look, e to the x, that's a solution. E to the 2x, that's a solution. So, all right, what do we do? Well, what we can do is say, okay, we'll convert this into our characteristic polynomial. So you have r to the 4th minus r cubed plus something r squared plus something r minus 6 equals 0. And we know that this has roots 1 and 2. Now, how do we know it has roots 1 and 2? Well, e to the x corresponds to a root of 1. E to the 2x corresponds to a root of 2. So, when we plug it in 1, what do we get? We get 1 minus 1 plus, all right, so let's do that here. 1 minus 1 plus a plus b minus 6 equals 0, which really tells us that a plus b equals 6. When we put in 2 to the 4th, 16, minus 2 cubed, 8. 2 squared is 4, so 4a. And 2 times b is 2b, or is it not 2b? No, it is 2b. Yeah, 2b and minus 6 equals 0. Well, 16, that's minus 14 if you combine the minus 8 and the minus 6, which tells us that 4a plus 2b has to equal, 16, subtract 14, it would be 2, but move it across is minus 2. All right, 2 equations, 2 unknowns. We can handle that. We've done this before. So, for instance, suppose we take our first equation and multiplied that by negative 2 and added it to the second equation. We'd have minus 2a plus 4a would give us 2a. Minus 2b plus 2b is 0. Then we have minus 12 minus 2 would be minus 14. So that tells us that a has to be negative 7. Now that we know what a is, we can plug that back here. So we have negative 7 plus b equals 6. So b has to equal 13. All right, so there we go. So we have a and b. So we'll just put that in a small box here. So a needs to be negative 7, and b has to equal 13. All right, so there's part A. We're done. Both part A. Now, part B says, look, what's the general form? Okay, now what's the problem? Well, we know 2 of our solutions, but there should be 4 total because it's a 4th order, which means we need to find the rest of the roots. So how do we do that? Well, we know a couple of things. So we can say, look, r to the 4th, so we're doing part B now, r to the 4th minus r cubed, and put in our values here, minus 7r squared plus 13r minus 6. Well, that equals, we know there's a root 1, so r minus 1, and then there's a root 2, r minus 2, and then something. If we know that something, find those roots, and then we're good to go. So how do we find it? Long division. Oh, yeah. So let's do, we might think, all right, we're going to do long division twice, right? Divide r minus 1, divide r minus 2. And actually, we can just do them at the same time, because notice that this part right here, you can write this as r squared minus 3r plus 2. So we're going to take this, divide it over, and whatever's left over goes there. So here we go. r squared minus 3r plus 2. Divide that into r to the fourth minus r cubed minus 7r squared plus 13r minus 6. So I have r squared. What do I need to get r to the fourth? R squared. So r to the fourth minus 3r cubed plus 2r squared. Subtract. So r cubed minus 3r cubed, so that gives us positive 2r cubed. Then we have minus 9r squared plus 13r minus 6. Okay, now I have r squared to get 2r cubed. We need what? 2r. So plus 2r. So that'll be 2r cubed minus 6r squared plus 4r. Subtract. We get cancellation. Minus 9 minus minus. So that's really plus 6. Gets us to minus 3r squared. 13 minus 4 is 9r. And then there's minus 6. So, okay, I have r squared. What do I need? To get to minus 3r squared, I need minus 3. And so we have minus 3r squared. Then we'll have plus 9r minus 6. And we subtract. We end up with 0, which is what we should get because these are roots. So that says this piece right here is r squared minus 3r plus 2. Now, how does this factor? Well, how does it? It probably does. I mean, they wouldn't be that mean, would they? Would they? Do we have two numbers that multiply together to give us positive 2 and add to give us negative 3? And the answer is, yeah, we do. What are they? So they are r minus 1 times r minus 2. All right. Oh, whoops. I can't believe it. I looked here. I should have looked here. This is r squared plus 2r minus 3. Yeah. Make sure you grab the right thing. I'm not grabbing what I divide by. I should have grabbed that. Okay. All right. So back to work, Steve. Come on. Two numbers that multiply together to give negative 3, add to give 2. Well, yeah, there are two such numbers. There's r plus 3 and r minus 1. And you can check, right? R squared, then you have minus r plus 3r is 2r, and minus 3. So, what are the roots? Well, there's the ones we knew about already, which are 1 and 2, and then the other ones were negative 3 and 1 again. So 1 is actually a repeated root. So probably we should write it as 1, 1, 2, negative 3. And once you know the roots, you can write the general form, and so here you go. So our general form, well, that would be e to the x. So we'll have some constant, e to the x. Then we have e to the x again, so we need to bump it up. Some constant x e to the x. Then we have the 2, so plus some constant e to the 2x. Then we have the minus 3, so plus some constant e to the minus 3x. And that's it. All right. Great. Cool. That worked out really well. Well, yeah, of course, because it's a problem on a test. It's designed to work out. All right, number 5. Lots of text here, but of course we see the Wronskian. So this is a Wronskian problem. So it says compute the Wronskian, w of fg, for the functions f of x equals x squared and g of x equals e to the 2x. Are these functions linearly independent, and why? So, well, let's just run through it. So for part A, this is the Wronskian of two things, and so we're going to have x squared and e to the 2x. So that involves a small matrix. So determinant of x squared, e to the 2x are our original functions, and our derivative is 2x, 2 e to the 2x. So we get here, going down, that would be 2x squared e to the 2x, subtract 2x e to the 2x. All right, multiply, add, subtract. And, well, okay, this is, we can clean it up a little bit. So, for instance, I can factor a 2x e to the 2x out. And if we do that, well, we're left with x from the first term, and we're left with just 1 from the second term. And there we go. Now, the key thing here, this is not 0, so linearly independent. So that's our answer for part A. So this is the y. So just to make it clear, we'll even just mark this is the y. It's not 0. So the Wronskian, really, you have sort of a yes-no question. Are you 0? Are you not 0? And that determines it all. So that's part A. That's not too bad. Part B. So it says, given two linearly independent functions, f and g, we can create a linear homogeneous second-order differential equation with f and g as solutions. So it's like, oh, okay, so this is how we can construct differential equations. See, so sometimes we're like, oh, I have a differential equation. Here, what are the answers? And now we're like, well, here are the answers. How would we find a differential equation that fits it? And it says, this is how you do it. And how do you do it? Well, you can do a Wronskian of f, g, and y. So we're thinking of y. It's a differential equation in y. So you have y, y prime, y double prime. So, all right, use this to find a second-order differential equation for the functions from part A, and divide out any common factors of the coefficients in the resulting equation. In other words, make it look nice. All right, well, it's a large wall of text, and then you realize, oh, it's just saying compute a Wronskian of 3 things. That's really what part B boils down to. So we'll do that. We'll compute the Wronskian of those 3 things. So here we go for part B. So we're going to compute the Wronskian of x squared e to the 2x and y. Okay, so we're going to have a slightly bigger matrix. The first row, 3 functions, x squared e to the 2x, y. Second row, 2x, 2e to the 2x, y prime, because the root of y is y prime. Third row is 2. Then we have 4, e to the 2x, and y double prime. All right. So now we have to just go through it. And I like to do that diagonal, so we go 2, 2, 2, 2, 2, 2. So we're going to have x squared times 2e to the 2x times y double prime. So, well, let's write it as 2x squared e to the 2x y double prime. Then we'll have e to the 2x times y prime times 2. So we'll write that as plus 2 e to the 2x y prime. And the last one will have y times 2x times 4 e to the 2x. So that'll be plus 8x e to the 2x times y. Good. Now, those are half of it. We still have to do another half. So, going the other way, 2, 2, 2, 2, 2. So, what do we have? Well, 2 e to the 2x times y. So, that'll be 4 e to the 2x. And we have to subtract. So, I'm going to put that right underneath the y term, just because they naturally go together. Then we have 4 e to the 2x, y prime times x squared. Okay, so that'll be 4x squared e to 2x, but subtract. So minus 4x squared e to 2x, y prime. And then, finally, y double prime times 2x times e to 2x. So, again, subtract. So minus 2x e to the 2x, y double prime. All right. So, well, we're most of the way there. We just clean it up a little bit. And, okay, what can we say? Well, everything has a 2. Everything has an e to the 2x. So let's factor that out. So we have 2e to the 2x. And now, what do we have? Well, with y double prime, we have x squared, and then we have minus x. So we'll have x squared minus x, and that'll be y double prime. Okay, how about y prime? Well, we factor out the 2e to 2x, so that's 1. So plus 1. Here, we have 2 left. We have x squared, so it'll be minus 2x squared y prime. And, all right, over here, well, we have 8, so we pulled out 2, so that leaves us with 4. So 4x, so 4x, and then down here, we'll have 2, okay, and so 4x minus 2y. Now, nothing's in common, and that's our Wronskian. Remember, we're setting our Wronskian equal to 0, so the answer is x squared minus x, y double prime, plus 1 minus 2x squared, y prime, plus 4x minus 2 times y equals 0. That's the answer. Now, what could you do if you were paranoid? So the claim is that this differential equation has x squared and e to the 2x as solutions. So if you were kind of like nervous, you're like, I've been in trouble before, right? Well, what you can do is just sort of plug in, okay, what happens if I try to plug in x squared? And does it work? What happens if I plug in e to 2x? And does it work? And the answer will be yes, as long as you haven't made a mistake. So it's a way to check your work. But for us, we're going to go on faith that we did it right and say, look, one last problem to go. Number 6. So consider the differential equation y prime equals f of y. So that means it's an autonomous differential equation. And f of y is shown in the picture below on the left. So here's f of y. And you'll notice we don't have an explicit expression for f of y. We just have to go by the picture. So, okay, all right. Find all the critical points, which are the same thing as constant solutions for this ordinary differential equation. Sketch the phase diagram. Classify each critical point as stable, unstable, or semi-stable, and give us a rough sketch of several solutions for the ODE below on the right. So here's this space for us to work in. Now, it's actually easy to find critical points, right? Critical points are zeros. So if we want the critical points, we're saying, look, so critical points would be f of y equals 0. Well, here's f of y. So to be 0 says look for where do you hit the axis. And we hit it at 3 points. So there are 3 critical points. All right. So our critical points, we can make a little note here, are going to be at, well, -3, -1, and 2. All right. Now, next up. I should say the minuses don't show up very well here, but that's okay. Next up, well, we want to do the phase diagram. And actually, we can just come here, say, okay, so here's our phase diagram, and we can just go straight down. So we have our -3, -1, and our 2. So how do we do the phase diagram? Well, what we look at is we say, where is our f function, positive or negative? So we see here, we're positive if we're up above the axis, we're negative if we're below. So we see that this is f of y is, below, so that's negative. F of y is above, positive. We're still above, so still positive. And we're below, so we're negative. So we can see from the picture what's going on. You know, negative, positive, positive, negative. Now, how does that translate? So be careful here. You know, you're like, oh, I'm coming in towards -3. Oh, that's the f of y, but what is the translation? If I see it's a negative value, that means I'm going to the left, to the left. If it's a positive value, I'm going to the right. So negative says I move to the left, positive, move to the right, positive, move to the right again, negative, move to the left. So there we go. So this is our phase diagram. Okay, so now we need to classify each critical point. So we can do that very quickly, actually, once we have the picture. So -3, we're pointing out. So that says if I'm -3, okay, I'm fine, but if I'm close to -3, I move away. So that says that -3 is unstable. -1, what's happening? Well, we're sort of going this way. So the arrows both point in the same direction. So I get close to -1 from below, but I move away from -1 above. So this is sort of half stable, right? You know, on one side it's stable, on the other side it's unstable, and we call this semi-stable. And then in 2, we see we're pointing in. Okay, so what is that? Well, that means that if we're close to 2, we move to 2. So that is stable. All right. So that's another part of our answer. And so the last thing that we haven't done is give a rough sketch. And for that, well, let's give a rough sketch. So we can draw the constant solutions. So, okay, so -3 is here. So that's one of our curves. -1, okay, that's there. And then +2 is here. All right. Now, from that, we say, okay, if we're below -3, we go down. So below -3, we're going down. So that says we're doing something like that. From -3 to -1, we're going up. So we're going to go up. All right. From -1 to 2, going up. So and then above 2, we go down. So we're coming down. So we're going to look something like that. And there we go. Now, of course, there's always the question, how many do you need to draw? And if you have a question like this, the answer should be enough to convince the person grading it that you know the different behaviors. So make sure you do the constant solutions and at least one in every one of the 4 parts. That should be sufficient. All right, there we go. That one was fun. We actually, you know, the nice thing about these problems is you don't actually have to do any, you know, integration or solve anything fancy. It's just saying, hey, what's going on? And so you can do them pretty quick. So fingers crossed, maybe we'll have one. Who knows? Well, we all will soon. All right. Hope you have a great day.